looking at the density of different metals. Here you can see Inconel, titanium, and aluminum, and then our composite, which is even lower than aluminum. And if we look at the strength, so this is at room temperature, we see the numbers here with composites not being 5 times lower than Inconel, definitely not, and also not so much lower than titanium, even with a what's called here QI laminate. So this means we have 4 orientation of fibers. We have fibers in the 0, plus, minus, 45, and 90 degree. I'm looking here at the yield strength at 180 degrees C for 10,000 hours. And why such a high temperature? Well, when you compress a gas, the temperature increases. And so having the ability to run a compressor at a higher temperature is actually a technical advantage. It's not a showstopper, but it's a technical advantage. There are possibilities to cool the gas between stages, but it makes the machine even more complicated. And so in this case of 180 degree, 10,000 hours, you can see that the aluminum has a significant drop down in their properties. Titanium, I haven't said it now yet, but titanium has another problem with hydrogen. It's called hydrogen embrittlement. And hydrogen embrittlement makes titanium unfeasible or unusable for pure hydrogen. I'm looking also at the fatigue limit here after 10 million cycles, and you can see there's quite a drop down in the strength for metals, a bit less for our composites, but still at the end, if we take a design value where we combine everything, so we take the strength and we take a knockdown factor for temperature and a second knockdown factor for fatigue, we get this number here. And as I said, the forces are induced by centrifugal forces, are induced by the density of the material. So what is really interesting is look at the specific properties. And the specific properties are the values measured divided by the density. And when you do that, you get these values here that are shown graphically on the right. And you can see the composite, no matter how you look at it, whether it's the tensile strength at room temperature at 180 degrees for 10,000 hours, at 10 million cycles, or the design value, which combines everything, you always see an advantage of about a factor 3. The reason I put the arrow compared to Inconel is because aluminum at these temperatures really doesn't offer very much at the end, and titanium is ruled out due to the hydrogen embrittlement. So we're left with a steel or with an Inconel, and there is in the API standard 617, Chapter 1, there is a restriction for the use of metals that have a higher yield strength than 827 megapascal, and they are prohibited for use in pure hydrogen. So even the values I'm showing here, which are the actual values that you have with standard Inconels, would be an alloy that would be too high in terms of elastic limit at room temperature compared to what the API 617 states. So this is even somewhat of an underestimation when you compare our composites to a metallic solution. I did speak a little bit about the layup. So the properties listed here are the properties you obtain when you take 4 orientations for fibers. So you have what's called a quasi-isotropic layup material, the same properties in all directions in the plane.